Good morning, students. Hope you all are doing good. So it's been a long time since I interacted with you all. Okay, most of you will be knowing me, but for those who have not interacted with me, my name is Sobernika. I have handled engineering chemistry for you. And this time, material science and composition lab. Almost half the syllabus have been completed by Hitaishi ma'am. So we will just go through some virtual labs of material science and composition. Okay, so let others join and then I'll begin. Till then, I'll just show your syllabus screen so that we know what we are going to do and what we have done so far. So if you can see in your syllabus, in MSc Lab, we have the first one, which is to study the microstructure of various ferrous and non-ferrous materials. Is it audible now, Bomik? Okay. So the first one is to study the microstructures for various ferrous and non-ferrous metals. And then the second one is to prepare this specimen for microscopic observation. Then the third one, to determine the strength and hardness of ferrous specimen, similar way for the non-ferrous specimen. Then fifth one, to study the effect of heat treatment process on the hardness and tensile strength of mild steel. Then to show the effect of different quenching media like oil, water, brine on the hardness of mild steel. Then to determine the hardenability of a specimen by Jomini and quench test. Then you have to determine the surface defect by liquid penetrant test. Then the determination of surface defect by magnetic particle test, to determine the internal defect by ultrasonic test, and then white pottery practical study and manufacture of glass. So these are the list of experiments that we have in this particular syllabus, and I'll be giving you an idea about all these. Okay, so my task is to get you aware with all these, either theoretically or practically, whatever is possible. Okay, so you must be knowing what is ferrous and non-ferrous metal by now. Yes, Ashnafi, thank you. So, what is the difference between a ferrous and a non-ferrous metal or a material? Sorry, give me examples of ferrous material and non-ferrous material. Okay, steel is ferrous. Then, yes, fiston ferrous means there is presence of iron or any forms of iron in the material. Okay, non-ferrous aluminium, nickel. Okay, so I'm going to show you a screen where there is difference between a ferrous and a non-ferrous metal. If you can see the screen, okay. So this is basic difference between a ferrous metal versus the non-ferrous metal. First, we will see the properties of ferrous metals. So ferrous metal contains iron as a component. All except stainless steel are corrosive. All the ferrous metal except the stainless steel are corrosive. And all the ferrous metals, they have this magnetic property because of the presence of iron in it, and they are not much expensive due to the higher supply of iron, and most are heavyweight metals. So these are the properties of ferrous metals. And when I say non-ferrous metals, the name itself indicates it is not having iron in it. Okay, so non-ferrous metals do not contain iron. They are non-corrosive. They do not have magnetic properties, and they're expensive because of the reduced supply. Because now Jay Mehta has put in the chat box nickel, aluminium. So they are all rare. It's getting these metals are rare. Okay, and they are mostly low weight metals. Okay, so this is a basic difference between the ferrous and non-ferrous metals. So now I will show you some videos on how we can prepare the specimen for metal testing, microscopic analysis. So this first video, there are two videos which I have. I have many videos, but regarding this microscopic testing, there are two videos. First, we will start with the macroscopic analysis. Macroscopic is visible, the one which you can see by naked eyes, and then we will move on to microscopic, which is using a hi-fi microscope. Okay, so first we will start with macroscopic. So I will show you as many videos as possible so that you can relate the concepts that you are learning easily. I've not shared the screen yet. So let me share it now. Okay, now the screen is visible and this video I'll play now.
Metallography Part 1. Macroscopic Techniques. Metallic materials are widely used in many areas of everyday life. How are they built up in their inside? Are there perhaps crystals to be found? And if so, how big are they? What kinds of crystals are there? What is their shape? And are there voids or inclusions? Metallography gives an answer. In this video, we would like to introduce the macroscopic techniques of metallography. Macroscopic means to investigate a workpiece over a comparatively large area. Doing this, only little or no magnification is required. Often the naked eye is sufficient to examine the material. As a first sample, we are going to investigate an ingot made from an aluminium alloy. To have a look at the inside, the material tester has to start with a raw cut through the ingot. She picks up the ingot and carries it from the laboratory to the mechanical workshop. The bandsaw machine has already been prepared. The ingot is positioned on the saw table so that the red laser marking line indicates the intended cutting plane. Clamping jaws fix the ingot securely. Then the bandsaw gently sets onto the block and cuts it slowly under intensive liquid cooling. It is important to keep the material as cool as possible to avoid changes in the material structure. That's it. The ingot has been sectioned. Back into the lab, not much is to be seen on the cross-section apart from the typical saw marks. In the next step, the material tester removes the saw marks by careful wet grinding with silicon carbide paper. On the one hand, this serves to produce a flat surface. On the other hand, the plastic deformations are removed that were generated by sawing. After the first grinding operation with coarse-grained paper, the material tester rotates the sample by 90 degrees and grinds it once more, this time with medium-grained silicon carbide paper. Here again, she uses sufficient flushing with water. This keeps the sample cool and prevents the abrasive paper from being loaded with material particles. Now, a flat, medium-ground surface has been created, but apart from the grinding marks, nothing special can be seen. Our sample reveals its structure only by the final etching process. After washing and drying the sample, the material tester dips the ground surface into a suitable etchant. In this case, the etchant consists of a mixture of different acids. Special care should be taken here. The material tester protects herself with a lab coat, special gloves and safety glasses. After half a minute of contact time with the etchant, she washes the sample thoroughly with water and gently wipes off the grey coat of particles using cotton wool. In the last step, she rinses the clean surface with alcohol and lets it dry under a hairdryer. Now the specimen preparation is finished. Beautiful bright and dark shimmering crystals can be seen. In technical terminology, these crystals are called grains. In the central and lower region of the sample, the grains are
Okay, so this is what I was telling when I said macroscopic analysis. The way in which she has prepared the surface, the crystals are visible even without any microscope, right? Magnifying lens, nothing was required. Just by the naked eye, we could see this crystal structure, a rough crystal structure. We get an idea. Okay, so let's move ahead.
comparatively small. They are hardly visible with the naked eye, but in the upper part, large individual grains may clearly be distinguished. But why are the grains only visible after etching? The reason for this is that the etchant structures the material grains on the surface according to their crystal orientation. Experts call it grain contrast etching. At lateral illumination, the individually structured grains reflect the light in different directions, and the grains become visible. As a second sample, the material tester examines a piston from a petrol engine of a passenger car. The procedure is the same as before. Careful sectioning under liquid cooling is followed by wet grinding with coarse-grained paper, then wet grinding with medium-grained paper, and finally the decisive step, the etching. After washing, cleaning and drying, fantastic crystals are visible again. It should not be concealed that these crystals, these grains, are not perfect and uniformly structured crystals, but so-called primary grains. Within the primary grains, many other very small crystals and also crystal defects may be found, but these can only be seen with appropriate microscopes. Virtually all materials of our world can be examined metallographically. To show part of that variety, we will look at some additional test pieces made from different steels. All of these samples have been sectioned first. Some of them are so small that they have been mounted in resin for easier handling. And all of the samples have been wet ground with medium-grade abrasive paper. This was done towards the end of the preparation, as shown here in the case of the tooth of a gear wheel. After grinding, not much is visible except from the typical grinding marks. As before, the internal structure will only be revealed by etching. But now the material tester uses a different etchant. This time it is nitric acid diluted in ethanol. She holds the mounted sample with pliers and immerses it into the etchant. After a few seconds, she takes the sample out again, washes it thoroughly with water, then with alcohol, and finally dries it with a hairdryer. Now the preparation of the flame-hardened tooth of a gear wheel is finished. In this case, the individual grains cannot be seen. They are far too small. But what may be seen very well is the hardened zone, which appears light, and the central soft and tough region, which appears dark. Next in line is the section of an induction-hardened cylindrical shaft. The comparatively soft core is much more affected by the etchant than the hardened surface layer. Clearly, the induction-hardened surface layer can be distinguished by its light color from the darker core. This section of a splined shaft is induction-hardened as well. As a result of the etching process, the outline of the hardened surface layer may easily be recognized. The dark area represents the core that has not been hardened. This is a tooth from a case-hardened gear wheel. The The surface region of the gear wheel has first been carburized at high temperature and then quenched. The etched sample shows the smooth transition from the carburized and hardened surface region to the softer interior. Weld joints can also be examined metallographically. In our case, the etching process takes a little more time and the analysis is more difficult. But by and by, the structure inside the steel plates, the position of the weld passes, and the heat-affected zones may be identified with a skilled eye. Even in everyday life, one meets metallography. At this hot-dip galvanized lamppost, the rainwater has acted as an etchant over the years. The large flat zinc crystals have been structured on the surface and can be recognized as so-called spangle. Even inside of a tin plate steel can, crystals are visible. The fruit acid of pineapples has etched the flat crystals of the tin coating. A natural and unintentional grain contrast etching process has taken place. On the outside, the tin coating is still unchanged and shines like new.
So this was about the macroscopic analysis, in which they are showing you a different metals and different purpose metals, and how they have been produced, how they have been uh, crystallized. Okay, hardening and softening. Hard crystals, hard metal is placed on the always the edges, so that the edges don't break easily, whereas the soft interior core, it is little softer when compared to the hard exterior one. Okay, so this was about the macroscopic analysis, and now I'll show you the microscopic part. So if you remember the steps of analysis, first what they did is they are going to wet grind it using a coarse sandpaper, then a mild sandpaper wet grinding, then etching it with any proper etchant, then alcohol wash, and then you're going to dry it, and then you can see it. Okay, that was the step. Now we will see what they're doing for microscopic analysis. Okay, here you go. This is a screen.
Metallography, Part 2. Microscopic techniques. Metallic materials are widely used in many areas of everyday life. How are they built up internally? Are there perhaps crystals to be found? And if so, how big are they? What kinds of crystals are there? What is their shape? And are there voids or inclusions? Metallography gives an answer.
Voids means any empty spaces within the metal structure. Okay, if you have a metal block and there are some air gaps, then it is called as voids. And inclusions, like if you have welded and you have put an extra piece inside it, that is inclusion. So to find out the internal structure, you can go for microscopic analysis.
In this video, we would like to introduce the microscopic techniques of metallography. Microscopic means to investigate a workpiece at higher magnification, usually with a light microscope. To have a look at the inside, the material has to be prepared properly, and this is how it is done. First of all, a small specimen has to be cut from the actual workpiece. The specimen is mounted in resin, ground in several stages, polished in several stages, and finally etched. Now the specimen is completely prepared and ready for microscopy. As a typical example, we are going to investigate a bar made from a steel used millions of times, the plain carbon steel C45E, with 0.45% of carbon. To start with, one of our material testers defines the intended sectional plane and marks it on the bar. In this case, it's a longitudinal section. Then he takes the bar to the abrasive saw to cut out a small sample. He fixes the bar securely, prepares the machine, selects the cutting parameters, and starts the first abrasive cut. Intensive water cooling and appropriate cutting parameters are important to keep the material as cool as possible. After finishing all abrasive cuts, the material tester picks up the sample and hands it over to his colleague. For further processing, the specimen has to be mounted in resin. To ensure that the resin will adhere well to the specimen surface, the specimen is placed in an ultrasonic cleaner bath for a few seconds. Alcohol and ultrasonic waves help to remove fat and loose particles from the surface. A short time under the hairdryer and the specimen is clean and dry. To mount the specimen, small plastic molds are suitable. The material tester picks up the clean specimen and carefully places it into one of the molds. The intended plane of examination is at the bottom. Then he pours liquid resin into the mold. A thin layer of grease at the inner surface of the mold acts as a release agent. This ensures that the cured resin can later be released easily from the mold. Now the mold containing the specimen goes into the light curing unit. Under the action of intense blue light, the resin polymerizes within half an hour. The resin has cured and embedded the specimen well. As an alternative to light curing resins, many other embedding materials are available. Each of them has its own advantages and disadvantages. Because the top surface is still uneven and slightly sticky, the material tester grinds it there until it is even. He uses a rotating water-lubricated disc equipped with coarse-grained silicon carbide paper. The circumferential surface is slightly ground as well to ensure a clean specimen. Now comes the most important part, the preparation of the intended plane of examination. Our material tester begins with comparatively coarse 180 grit abrasive paper. He makes sure to press the specimen calmly and evenly onto the abrasive paper, compensating the tendency for the sample to tilt. He also makes sure not to grind his fingertips accidentally. Now he has achieved an even, relatively rough surface. The specimen is ready for the next step with finer paper. He inserts a new 320 grit abrasive paper onto the disc. Rotating the specimen by 90 degrees leads to new grinding grooves perpendicular to the old ones. In this way, the material tester can easily check whether the old grinding grooves have been removed completely. It is important to use sufficient water flushing during grinding. This keeps the sample cool and prevents the abrasive paper from being loaded with material particles. Grinding continues with 600 grit and 1000 grit abrasive paper until an immaculate, finely ground specimen has been achieved. The specimen is now ready for polishing. An absolute prerequisite for polishing is a thoroughly clean specimen. The ultrasonic bath and running water help to remove any residue from the ground surface. Otherwise, hard particles might be pressed into the polishing cloth and scratch the surface. Hands should be washed as well so that no unwanted particles find their way to the sample and the polishing cloth. Now the material tester can start with the first polishing operation. He chooses a polishing disc equipped with hard cloth of low resilience, moistens the cloth with a suitable lubricant, and adds 2 splashes of diamond suspension of particle size 6 micrometers. Under counter-rotating motion, he presses the specimen with high pressure onto the polishing cloth. The diamond particles have settled on the cloth and are now abrading the surface. After about a minute, all grinding grooves have been removed and the specimen surface already has a shiny appearance. But still there are many fine scratches to be found, resulting from the 6 micrometer diamond abrasive. To remove them, the material tester washes the specimen and his hands again very carefully and polishes the specimen for a second time. Now he uses a softer short nap polishing pad, finer diamond suspension of 3 micrometer particle size and less pressure. After the second polishing operation, the specimen surface has an almost mirror-like appearance. No more scratches can be seen with the naked eye. Nevertheless, the specimen has to be cleaned again and go through a third and final polishing operation. This time, 50 nanometer aluminium oxide abrasive is used. Only then is the surface prepared to a sufficient quality. At the end of the mechanical preparation, special care has to be taken to clean the specimen properly. On the one hand, all abrasive particles have to be removed. On the other hand, the freshly polished surface must not be scratched or damaged. Under running water, the material tester gently wipes the specimen with cotton wool, thoroughly rinses it with alcohol, and dries it with a hairdryer. From now on, the sample is called a metallographic specimen or microsection. Judged with a naked eye, our metallographic specimen seems to be well prepared. It is now allowed to go under the microscope for the first time, or rather onto the microscope. In fact, the design of typical metallographic microscopes is inverted. Inverted means upside down. The microscope objective is not facing downwards as usual, but upwards. This offers the advantage of simply placing the metallographic specimen on top of the microscope stage. The prepared surface faces downwards. Using the built-in digital camera, the polished specimen surface can be observed on the computer monitor. In the polished state, there isn't much to be seen in this material. Only some elongated non-metallic inclusions can be observed, but if these inclusions are of special interest, then the polished state is the perfect one. Inclusions may best be seen here. However, if one wants to see the crystals, the grains and grain boundaries, then the microsection has to be etched. To do this, our material tester protects himself with a lab coat, puts on safety glasses, and pours the etchant into a small glass bowl. The etchant consists of a solution of 10% of concentrated nitric acid in alcohol. Now he turns on the water tap, picks up the freshly polished microsection with gripping tongs and immerses it for a few seconds into the etchant. Then he rinses the microsection thoroughly with water and afterwards with alcohol. The hairdryer is again used for drying. The excitement increases. Was the etching time correct? Has everything worked out fine? At low magnification, not much can be seen, which looks characteristic. The tester gradually switches over to higher magnification. In between, he focuses and adjusts the brightness. At medium magnification, light and dark areas become visible. At comparatively high magnification, in some of the dark areas, fine stripes may be recognized. The microstructure in the darker striped regions is termed pearlite. Pearlite consists of thin alternating crystals of ferrite and cementite. The white regions are ferrite crystals. They consist of almost pure iron. Great! The etching has been successful. In a similar manner, virtually all materials of our world may be examined. This is the plain carbon steel C80 with 0.8% of carbon. Only pearlitic regions with their characteristic alternating layers of ferrite and cementite can be seen. And this is the plain carbon steel S235 after a color etching. It only has a low carbon content. The relative amount of differently colored ferrite crystals is high, the proportion of pearlite regions low. The variety of materials is huge, and each material needs its own individual preparation method in metallography. The preparation is often not conducted by hand as shown here, but by automatic methods. This saves time and money. The principle, however, is always the same. Sectioning, mounting, grinding, polishing, and etching.
Okay, so now I hope that you have understood how a microscopic and microscopic samples are prepared. Okay, so in this way we can analyze any ferric and non-ferric materials, but our main target is the ferric materials. and the ferrous materials which have any impurities in them, or how much amount of ferrous is there in that, everything can be determined with microscopic analysis. Even the defects, some stripes, everything, okay, the minute structure can be very well understood using a microscopic analysis. So this was your first experiment. Okay, so to study the microstructures of various ferrous and non-ferrous materials, so and to prepare the specimen for microscopic observation. Okay, so this is how it is done. So the first two experiments are almost delivered by me, so it is I hope you have understood it. So when we meet in the next lecture, we will talk about the strength and hardness. Okay, so before I end the session, can you let me know how much of experiments you have already understood or you have already been taught out of 12? Out of these 12, were you taught any experiments already, either practically or theoretically? Okay, are you sure nothing was taught to you because you had MSc labs? Okay, fine. No problem. So, but this is clear to you? You are able to relate it? Okay, no issues. Okay, fine. So, but if I'm going to continue this way, will you be comfortable? Okay, fine. And yes, of course, I'll be taking the remaining experiments also. So I'll need hardly 4 to 5 sessions, and then I'll show you all the videos and whatever virtual links I have. So we will study each and every experiment this way. Okay. So those who have not typed your name in the chat box, so you can just type your name and roll number in the chat box and exit the meeting. Type your name and roll number in the chat box and you can exit the meeting. Okay. So if you have any queries, you can let me know. Thank you, everyone.